continue basically where we left off the other day. We're still in the same section in our textbooks. They do exponential and logarithmic models in one section, and we've divided it up into 2 days here. So let's see, hopefully that will be on. I do want to just mention that, again, in case you've forgotten, that our final exam is next Wednesday. And that's December 18th. Your day to shine, hopefully. And it will be at 10:30 in the morning in this classroom right here, North 405. Okay. Your project, your final project, you can either put it in your folder today. It's either due today or Friday, whichever day works for you. So if you have it today, great, throw it in your folder and I'll grade it for you and get it back to you for Friday. And you have a quiz on Friday. And you're going to have 15 minutes for this quiz. So I will call the time at 10, what would it be? 10:55. I will call the quiz over. So if you think you're going to need more time than 15 minutes, come in a little earlier. You don't have any classes scheduled after 10. But let me just tell you what's going to be on the quiz. You are going to have one logarithmic equation to solve and one exponential equation. That's it. You're going to have 2 equations. Okay. So as long as you've done your homework for logarithmic and exponential equations, I believe that was class 37, you should be absolutely fine. I'm not going to pick the hardest problem that you could possibly had to do for homework. I just want to make sure you know how to solve exponential and logarithmic equations. Now, we started doing some of that on Monday's class when we were solving for finding the different values of time for the half-life problem and the number of bottles of water. So we've been doing this all along in class, and we'll do more of it today. It's just that that's the thing I want to make sure you know how to do before you leave today. Anybody in here taking chemistry? One person? Anybody else? Okay. Yeah? No, you had 3 hourly tests prior to the final, right? Which you were allowed to bring in 1 page both sides. Hopefully you save them because you're allowed to bring in 4 pages. So you can take the page, both sides from each of your tests if you still have them. And then we've only covered about 3 or 4 classes since the last test you've had. And you have another whole page to throw anything else on you want. Okay, so no, you're allowed to bring in 4 pages back to back for the final. Okay, any other questions? Okay, so let's take a look at today's material. I've got the wrong lecture up here. I meant to get 40. Okay, here we go. So today we're going to look at applications that involve logarithms, and logarithmic functions are used to scale really large numbers or really small numbers, okay? So if you take an astronomy class or you take some biology or chemistry classes, in particular chemistry classes, where you're looking at pH levels, you often will bump into logs because astronomy involves really large numbers and chemistry involves really teeny numbers, okay? So we're going to look at some common logarithmic functions, some models for common logarithmic functions. And the first one we're going to look at is the Richter scale. I think many of you may have heard of the Richter scale. It determines the strength or the magnitude of earthquakes, okay? We're going to look at finding the pH of a solution. So Sam, for your chemistry class, this will help you out. And then the decibel scale, which measures sound intensity. Okay, so when you think about when you put those little earbuds or your headphones on, it might be interesting if you can find an app that measures the decibel level, because I have a funny feeling that a couple generations from now we're going to have a lot of deaf people because people keep turning up those I mean, this is just my own personal concern. When I can hear my daughter's earbuds and I'm in the car and she's in the back seat, I know it's too loud. Okay, and there seems to be this increasing need to have it louder and louder just to hear it. but there's a certain level where you actually can cause ear pain and then ear damage based on the decibel level. So I don't know if there's anything out there like a decibel app, but that might be interesting to look at. Ben?
I think for pop music hasn't actually gotten better. So.
It's just gotten louder?
Yeah, it's recorded a lot louder.
Wow, interesting. Well, did anybody ever notice like commercials, like if you're watching a TV program and the commercials come on, they're louder than the program. Most of the times I just have the closed caption on. I don't even like listen because it's just ridiculous. Anyway, so let's take a look at a couple of models today. This first example I put together a few years ago. I was doing some research on earthquakes and magnitudes because I knew that it had a log application, and I was reading about different ways that scientists measure magnitudes of earthquakes, and they have these things called seismographs that look like these, like, you know, almost looks like a lie detector type of test, these squiggly lines, right, going up and down. And there's something called S waves, and I read a lot about it at the time, and how you look at these and read these graphs. But I've forgotten a lot of what I read back then. It was probably 4 or 5 years ago that I read about this. But if you're trained, this is the type of reading that you would look at. You would read these graphs to determine the value or the magnitude of your earthquake. Now, if you were picking up a paper today and you were going to look and there was an earthquake somewhere and you were looking at the number that's reported for the earthquake, what type of number might you see? What that would measure the strength or the magnitude of an earthquake? What type? Up to 7? So, okay, well, just give me an example of what you might see. 5.2, okay. Another example? 6.8. There have been bigger ones, yeah. What do you think? What does anybody know the most recent earthquake? I mean, there's earthquakes happening all the time. We can't even feel them. Do you remember last year we had one here? I remember I was in my bedroom and I thought I was like hallucinating, like the wall looked like the wall moved. I'm like, whoa. And then I found out that we had a little baby earthquake here. Yeah, but like, what was like the most recent, like most catastrophic earthquake in that you remember? The one in Japan at the nuclear facility, right? Anything since then? No? All right. Well, would you ever see something like this, 112 for an earthquake? No, no. How about this, -2 for an earthquake? No. So, you know, what might you see, 8.2? Okay, so these are some of the common readings. So let's learn a little bit about these numbers and how we derive them. Okay, so it looks a little scary at first when you see some of these formulas, but a lot of the letters are just standing for constants. Now, there's actually another scale that's been invented since this German man named Richter developed this particular scale. They actually use another scale today, but since this is what's more common for most of us, and this is really what's reported most commonly in the literature. So the Richter scale defines the magnitude M of an earthquake, and this is how they define it. So the magnitude is equal to the log of two numbers. I is the intensity of the earthquake, and that's what's measured by this scale here, this graph. And S is a constant. It's the intensity of what they call the standard earthquake. And that's the smallest possible earth movement. So that's just a constant in the denominator for all of these logs. So this was a pretty famous earthquake in the history of the US. In 1906, San Francisco burned to the ground. It was totally destroyed by an earthquake. And the magnitude of that earthquake was 8.3 on the Richter scale. Okay. At the same time, because the waves traveled out through the Pacific, in Japan, they experienced an earthquake that had a magnitude of 4.9. So clearly, as it traveled from San Francisco west out to Japan, the intensity got smaller and smaller. Okay. So sometimes people, like, we look at numbers like 8.3 and 4.9, we say, what's the big deal? 8.3 isn't that much bigger than 4.9. 8's not that much bigger than 5. But remember, we're dealing with a different scale. We're dealing with a logarithmic scale. So let's take a look at how many more times the earthquake in San Francisco, how much bigger it was in terms of its intensity than the one that hit Japan. So let's take a look at these two equations, and we'll just put a little subscript on them, one for San Francisco and one for Japan. Okay, so we'll start there. So we know that the magnitude of the San Francisco earthquake is taking the log of two numbers, the intensity, and we'll put a little subscript on that, the intensity of the San Francisco earthquake divided by this standard value for the intensity of what they call a standard earthquake. And log the intensity for the Japanese earthquake divided by this standard. Okay. So we do know one of the values for these numbers. We know the magnitude of the San Francisco earthquake because it's given to us by this number right here, 8.3. That's how it was measured on the Richter scale. 8.3 is equal to the log of the intensity of that earthquake divided by S. And we know the Japanese earthquake was 4.9, and that equals the log of the intensity of the Japanese earthquake divided by S. Okay, so as with all of our log equations, when we want to solve log equations, we write them as exponential equations because they're a lot easier to work with. We know what the base is on this log because we don't see it, and we don't see ln there, so what's the base here? 10. This is our common log. So we know 10 raised to this, the answer to a log is a power, it's an exponent. 10 raised to the 8.3 is equal to this thing, the intensity divided by S. And similarly, we transform our log, here's our log equation, and all we did was change it into an equivalent exponential equation to help us solve this problem. We're going to do the same thing here. So if I want to turn that logarithmic equation into an exponential equation that's equivalent to it, can someone help me do that? What would it look like? 10, because the base is 10, it's not there. So we understand it to be 10. The answer, as Adam said, is the exponent for 10. 10 to the 4.9, Adam, is in the right side? Right, divided by standard. Okay. So our question asks, how many times more intense was the San Francisco earthquake to the Japanese? So what we're doing is we're dividing these two numbers. We're dividing these two numbers. So if you take the right-hand side, the intensity of the San Francisco earthquake is this, and if you divide it by the intensity of the Japanese, oops, that's a J there, sorry. Let me get my little eraser out here. And notice that when you divide these two, your S's will cancel. So you have the intensity of the San Francisco earthquake divided by the intensity of the Japanese earthquake, which is what you're asked to find. And the intensity of the San Francisco earthquake is 10 to the 8.3. And the intensity of the Japanese earthquake is 10 to the 4.9. So lo and behold, you finally have a reason to use one of your exponent rules that you learned a while ago, and then we reviewed it quickly at the beginning of this year, that when you divide with the same bases, what do we do with the exponents? We subtract them. So this becomes 10 to the 8.3 take away 4.9, which is 10 to the 3.4 if I did my subtraction right. Okay, 10 to the 3.4. So 10 to the third is what number? 10 to the third. 1,000, right? 10 times 10 times 10. So let's see what 10 to the 3.4 is. Let's see. So we got to clear all this out from my last class. 10 raised to the 3.4 is 2,511, approximately 2,512. So even though the numbers didn't look like they were changing very much, the earthquake in San Francisco was 2,500 times more powerful than the one that reached Japan on the same day. Okay? So the moral of the story is, if you're trying to compare the sizes of two different earthquakes, look at how we finally ended up, what we finally ended up doing. You're not going to have to go through, and nor will you remember all this mathematics. But if you had the values of two earthquakes and you were trying to figure out how much more powerful one was than the other, your base is 10, and all you do is subtract those two Richter scale numbers, and that will give you the factor of how many more times one was more powerful than the other. That's the end result. Okay, 10 to the 8.3, which was the Richter scale value for the San Francisco, and subtract from that the Richter value for Japan. Okay, yeah? Yes. Use that as your exponent? Yeah. No, you mean use 10 as your base, not the log. Yeah, yeah, that would be fine, because I know that you were just getting that from your notes. That's fine. I mean, in the end, this is all I ever do when I'm like reading papers or I'm looking at just because I've done this a lot. I mean, I could do all the mathematics, but why bother? There's an end result that's a model. So here's your model. Base 10, and you subtract your two Richter scale values. So the important thing is, when you're looking at changing the value of your magnitude by just one, that corresponds to increasing the intensity of your earthquake by 10 to the 1, or 10 times. So if your numbers have a difference of 3, then it's 10 to the third, 1,000 times more powerful. If it was 10 to the fifth, right, then it's 100,000 times. So if you have an earthquake that measures, say, 3, and one that measures 8, that's 100,000 times more powerful. So every time you see a change of 1 on any logarithmic scale, it changes by a factor of 10. Okay, and that's what exponential growth means. I mean, if you just think about this function for 1 minute, 10 to the x, for each increment of 1, whether you're looking at time or whatever you're looking at, your x value changing by 1, 10 to the zeros, 1, 10, 100, 1,000, 10,000, 100,000, okay? That's what defines logarithmic growth, exponential growth, is instead of like with a straight line, you add a number from one value to the next for each unit increment you have. With exponential growth, it's getting bigger by a constant multiplier, a factor of 10. So that's a difference. If this was a straight line like this, 10x, versus 10 to the x, if it's just a straight line, all we're doing is saying 0, and we're adding 10, a constant additive as we go up, which, as you can see, isn't growing nearly as fast as multiplying the previous number by 10. That's a major difference between linear growth and exponential growth. Okay? That's why, even though they may start off very similar, that it doesn't take too long for your exponential growth to really outpace any kind of linear growth. Okay, so that's the how you use these formulas for earthquakes, and you'll probably have a couple of questions on homework with this. The next thing we're going to look at is pH level, and let's just review a little bit about the pH scale, because you may all have different knowledge of pH. Okay, so what does pH measure? It measures, and this is what is hydrogen ion concentration? Well, I talked to one of the chemistry teachers yesterday, because I was kind of curious about this versus just reading you a definition. And does anybody know what the pH level is of water? Close. 7, right, Sonia? Right? And water is H2O, means you have 2 hydrogen ions and 1 oxygen. And she said this is how it breaks up. You have your hydrogen ion, and then you have your hydroxide ion, OH is hydroxide, and the plus and the minus sort of undo each other. So I said, and what the reason I asked you this question is I did A and B, problems A and B, and I looked at the answers. And I said, oh, the smaller your hydrogen ion concentration, the more basic your solution is. She said, yeah, absolutely. And I said, oh, well, I want to understand that even more. What about how do you make something have more hydrogen ion concentration? How do you make it be more acidic? So what do you think of as acidic? Vinegar, like, yeah, acids, right? Like acetic acid, vinegar, like grapefruit, citrus, right? All those things have acidic properties. What do you think of that may be what we call basic on the other end of that scale? Bleach, yeah. Ammonia, bleach, right? Baking soda, right? Have you ever tried putting if you've had like the little terminals on your battery, right? Getting all like white with acid, and you throw a little baking soda with water on it, it kind of like neutralizes it, right? Well, I used to do that when I had old crummy cars, right? I mean, there were those days. Now my cars are only 10 years old, but they're not crummy yet. All right, so, you know, there's ways of working with acidic and basic, and people always think acid bad and basic no, but ammonia and bleach are just as harmful as some type of acidic acid or some type of acid you might be using. So you got to be careful. You always got to wear gloves. All right, so I said to her, and this is what I took some notes on because I was curious and I wanted to show you. I said, okay, so I want to see water, which is neutral. Here's our water. She said, so you could add to any aqueous solution. This is how chemistry teachers talk. Aqueous just means it's a water solution. If you were to add acetic acid, which looks like this, CH3 COOH. And she says this looks like this, carbon with 3 hydrogens attached to it. I didn't do that right, but so this looks like a little bit of organic chemistry. And then you have your plus, your COOH with the minus. So I said, oh, so this is like your water, and they undo each other. So you're adding more hydrogen ion to it, ions. And she said, yeah, you're really fast. You're quick. And I said, oh, good. I understand a little bit more than I did just doing the math. So you're adding, when you add things like this vinegar or acetic acid, the compound, the molecule actually adds more hydrogen ions to the solution. So your concentration's getting more concentrated with hydrogen ions. So anyway, I don't know if that helps or not, but Sam, you're going to be in chemistry and you'll be looking at this soon. So hopefully you can tell me if that helped you. So that's why that's one of the reasons they have 107 as a prerequisite or co-requisite with the chemistry classes, is because of the logs that you deal with in chemistry. Okay, so let's take a look at this. We say that if your pH is less than 7, then you have an acidic solution, and if your pH is greater than 7, it's called basic. Okay, and this is the formula to determine pH. It's the opposite of the log of hydrogen ion concentrations. And the numbers that you put in here for hydrogen ion concentrations are really small numbers. Okay, and so when we convert, we take the log of really small numbers, it becomes a number that we're used to looking at, like 7 or 8.3 or 2.4. Okay. That is, moles per liter is a chemical unit, and you have to study chemistry to understand moles. You know, liter is a volume, like a, right? Moles is one of the units that they use to measure this. So many moles per molecule, something called Avogadro's number or something. It's this very small number, or very huge. I can't remember. I think it was something like 10. It was either to the some number times 10 to the negative 23 or 23. I can't remember. Have you had chemistry? Sam? Negative 23, yeah. I took chemistry in high school and then my first year at UMass, and so I'm going back a long way, but that's kind of what I remember. Okay, so determine if this, let's figure out whether shampoo is basic or acidic. So here's a hydrogen ion concentration. Now, if you wrote that out, it would be 0.0009074. Okay, really small. Okay, so we substitute in our formula. This is just a plug-in kind of day today where we're just plugging in into our formula, and then we're using our calculators to help us out. So pH numbers, before you even start to put this in your calculator, let me just put brackets right here for a minute. pHs are always positive numbers. So if you're taking the opposite of a log, what must this log be? What kind of number? If pH is positive and you already got a negative here, what kind of number must the log be? Negative, right? Think of your simple log function. Just like your parent function for x squared and your parent function for a straight line, your log function looks like this. Okay, that's what your log function looks like. It goes through 1, 0, and it goes through B1, whatever your base is. So in this case, our base is 10, so it would go through 10, 1. So I'd probably be a little bit further out on this scale, because this one would look a little more like this. Okay, so it'd be out here at 10, 1. So look, you're some really, really teeny small numbers. So you're somewhere in here. Here's your value of x. When you come down, you can see that your y value is negative. Your log is negative. So anytime you have a number, a log, where you're taking the log of a number between 0 and 1, you're going to be below the x-axis. You'll always be negative. So let's take a look at what this looks like in our calculator if we do this. So it's basically just using your calculator, and that's why for some of you that have come through our program, and particularly Sandy, she had you use your calculator with all these formulas you had to put in there. So let's see, log, and it's going to be 7.4. 7.4 times 10 raised to the negative 10. And remember, your negative button's down here, negative 10. Close your parentheses, and there you go. And then you want to change the sign of that number, right? So you change the sign. And there's your pH value, 9.13. Because you got negative 9.13076828. And when you take the opposite of that, you get a positive value. So that's pretty basic. Your shampoo is very basic. Okay, so your shampoo is basic. How do you know it's basic? Because 9.13 is greater than 7. 7 being your neutral point. So again, it's just plugging in the information you're given into your formula, and you get the pH out. What if we go the other way? Let's take a look at some nice red, and as I would say in Boston, lager, right? Nice red lager, okay, which most of you can't have yet because you're not 18, 21, sorry, all right? So, oh, I wish, huh? A month and a half? Oh, congratulations. So red lager has a pH of 4.1. So pH of 4.1 makes it acidic. So you know whatever answer we get for the hydrogen ion concentration has to be bigger than this number, 0.6074, because the more hydrogen ions you have, the more acidic. So your answers, even though it's still a really small number, it's going to be bigger than 7.4 times 10 to the negative 10. Right? So let's solve this equation. So now here's our equation. The pH is the opposite of the log of the hydrogen ion concentrations. We know what the pH is, so that's not what we're solving for now. We're actually solving for the hydrogen ion concentration. So this is what we want to isolate right here. We want to get H plus all by itself. So to undo a log, we convert it to an exponential equation. So just like we did at the beginning, we take that log, it's base 10. So we write our base 10. The answer to our log is our exponent. And this is how we solve the problem. Okay. So 10 to the 4.1 equals the opposite of the hydrogen ion concentration. So to get the hydrogen ion concentration, you want to take -1 times 10 to the 4.1. 1 divide or multiply both sides, excuse me, by the hydrogen ion concentration. So let's throw that into our calculators. So we have -1 times 10 raised to the 4.1. That doesn't look right. Oh, I know what I did. Yeah. I forgot. No, I forgot my my log property. Ah, there's no way it can be that. So yeah, divide by -1, just like if we were solving this like a linear equation. If this said 4.1 equals -x, you would divide both sides by -1. So let's divide both sides by -1 to get -4.1 equals the log of the hydrogen ion concentration. And now we convert it to an exponential equation. So we transform this into an exponential equation. We know its base. The base of the exponential is 10. Our exponent is -4.1, and that's going to give us our hydrogen ion concentration. Okay. We know it's got to be some small number. We can't be having the numbers that we just got a minute ago. So let's see what it is. Let's clear this out. 10 raised to the -4.1 is, there we go. But notice it's only e to the -5 this time. What was it before for the hydrogen ion concentration? E to the -10, right? So this is much bigger. It's much more concentrated, even though it's still a small number. So the hydrogen ion concentration is 0.0000794 approximately. Okay, so there's a hydrogen ion concentration. So similarly to your magnitude, your scale with the Richter, excuse me, the magnitude of the earthquake, if your pH drops by 1, then that means you have 10 times less concentration of hydrogen ion. Just keep track of that little e to the negative number. That's how you can, whatever that's how you're going to be dropping by a power of 1, because this will go from -10 to -9 to -8. Okay, so notice this was 9 and this was 4. Okay, not exactly 5 whole units, but this dropped power's dropped, okay, from -10 to -4.1. Okay, so let's take a look at decibel scales, and then I'm going to set you loose on your group activity today, which is kind of fun. It's called stellar magnitude. Ooh, well, you know, star light, star bright. How's that go? Something about, don't you know some of these like nursery rhymes? Star light, star bright, something in the sky tonight, or no? Nobody in here in early childhood, Ed? First star, thank you. I figured someone would have to know that, especially someone who might have a grandson. Thank you. I'm glad you stayed today, Sonia. I wouldn't have remembered that. The decibel scale was designed to reflect the human perception of sounds. The decibel scale, like the pH scale for acidity or the Richter scale for earthquakes, is logarithmic. Noise levels are measured in units called decibels, and we use little d, capital B. That's the unit for decibels. And it was given this name in honor of Alexander Graham Bell, right? Invented the telephone. So average conversation levels are about 50 decibels. And when I listen sometimes to the these videos back, I don't think I'm speaking at 50 decibels. It always seems pretty loud, and I think it's because you're all out there versus like right in front of me. But anyway, maybe I'm just loud anyway, who knows. So the average conversation is 50 decibels. So that kind of just gives you a frame of reference. Like if you just talk, you're not whispering, just regular old conversation, about 50 less decibels. Okay, so here we come with some more formulas and numbers, but nothing that should be too scary to you now, because You've seen logs and you've seen these equations already. But very similar to the earthquake equation, they have I sub naught, which is your standard reference sound. And it's the faintest sound ears are able to detect. And that's sort of used like a constant right here in this formula. Okay, and we let I represent the intensity of the sound. The units for measuring sound are watts per square meter. That's the units for sound. Then the noise level of that sound is measured in decibels, is defined to be 10 times that log. All right. So this is unitless. This has no units on it. I divided by I sub naught. They have the same units, so they're unitless. Gives the relative intensity of a sound when it's compared to the reference sound, which is the very faintest. So an average conversation is 50 decibels. That's how much, well, I don't want to give away the answer yet, but that's compared to the faintest sound detectable. Okay. So if I over I sub naught equals 100, let's calculate what the noise level in decibels will be. So in other words, if we knew that the intensity of a sound compared to the faintest sound was equal to 100, so it was 100 times more powerful, what would be the decibel level? So let's calculate the noise level in decibels. Okay, so all we have to do is we're trying to calculate N, and where we see this expression, we're going to replace it with the number 100. So 10 times the log of 100. Okay. And we know that the log of 100 is log base 10. Log base 10 of 100 is how many zeros are after the 1, 2, because it's 100 is 10 square. Log base 10 of 10 square. These guys undo each other. We just bring down the exponent. So we got log of 100 is equal to 2. So we bring that down here, and we get this decibel level, 20. Okay. So let's see, how does that work? Decibel level 20, and a noise, that's our noise level, and whatever sound we're listening to is 100 times more than the reference sound. So 20. So I wonder what the relationship is. Well, let me try another problem. See if I can figure out a pattern here. 1,000. What if we increase I over I sub naught to 1,000? So it's the same exact formula. We throw 1,000 in for I divided by I sub naught. And what's the log of 1,000? Common log of 1,000. 3. Because 1,000 is 10 to the third. And we're just going to lift off the exponent. 10 times 3. So there's our decibel reading. So 20 decibels if you're 100 times more intense than the reference sound, and 30 decibels if you are 1,000 times. Anybody want to make a guess as to how many more times the average conversation, how many more times intense it is compared to this reference sound if it's at 50 decibels? Found a little pattern yet between the answer and I divided by I sub naught? Half it. Well, half of 20, well, half of 20 is 10. Well, remember our average conversation, Adam, was 50 decibels. Right? So 20 decibels relates to 10 square or 100, right? Right, here we go. 30 went to 10 cubed or 1,000. What do we think 50 would correspond to? 10 to the fifth, right? So if you're just looking at this number here, your tens digit, so that's 100,000 times. So this faintest sound, probably my ears wouldn't hear it, okay? But just in average conversation, 50 decibels is 100,000 times more intense than the faintest sound detectable by the ear. So what about a typical rock band? And this is the intensity that they play at. 10 to the negative 1 watts per meters squared. So that's the value of I. So I want you to try doing this calculation. Okay. See if you can do something with that. And I'll help you out. Some of you may get stuck, some of you may not. So that's the average or typical rock band. Decibel levels of 130 causes ear pain. Now, I don't know if anybody in here is a football fan, but a couple of Monday nights ago, there was a game in Seattle. Seattle Seahawks. And who were they playing? Was it the Saints? The Saints, all right? And they had broken a record a couple of months ago where they recorded the decibel level in the stadium to be 134 or 131 decibels or something. So that night, they were trying to break the record, and they kept trying to get the crowd, and there was like 124, 125, and then I fell asleep. So I don't know if they actually broke it or not. Did they break it that night? But all I could think about was this lecture, because I remembered the 130 as being causing ear pain. So then I thought about, and this will be for any of you who are thinking about engineering or whatever. So I don't know, maybe this is just the way people like me think. So I'm thinking, how do they measure that? Here you have this huge stadium. Where do you go to actually measure the decibel level, or does it matter where you go? In other words, if I'm in the audience going, yay, Seattle's, oh, am I going to get the intensity of 130 decibels in my ear, or is it somewhere out there in the stadium? Do you know, Ben?
Right above the stadium. If you think about like at a concert, they usually have like stacks of PA system, like the speakers. If you're standing right up front, you're not going to get the loudest sound. But if you're standing like right in the middle of the audience, that's where you're going to get the
middle.
sound.
The middle is the loudest. So would it be in the middle of the stadium?
It'd be like above the stadium.
Above the stadium in the middle.
It's a cone, so to project everything out like this.
Okay, so then, you know, I went to one of the other math people, and we were talking about the shape, and it was elliptical, and trying to figure out where the sound bounces and everything. So unbeknownst to me, I went to see Ian, and we were talking about this, and he said, have you seen what I put on my Math 108 online course? I said, no. He clicks on a link. He had, from that night, there was a guy down in front of the end zone, right? And he had the whatever machine they're using, and this guy's like this, come on, louder. And the guys in the crowd are going, whoa, and they're trying to get louder, and they're trying to get it up, and I'm like, that doesn't seem very scientific to me, that he's like in this one spot in the end zone. I couldn't believe that that would be the one spot where it would be the loudest. So I've got to talk to an engineer to see how they actually measure this decibel level. But anyway, you may not be interested in any of that, but I kind of thought it was interesting, given that, you know, I knew I was going to be talking about decibel levels with you in a few days. So here we go. We're almost causing ear pain. If you've ever been to concerts, I think some of you may have experienced these. If you were in, what are you saying? All right. So how many orders of magnitude? Now, when you read that word, orders of magnitude, that means powers of 10. That's all orders of magnitude mean. More intense is the sound of a rock band than the average conversation. So the decibels for the average or typical rock band is 110 decibels, and the average conversation is 50. So that's 60 decibels. And as we just saw, this number becomes the exponent for our 6. So that means it's about 1,000,000 times more powerful than the average conversation in terms of the sound intensity. Okay, so you have about 23 minutes to work through just about anything you could imagine having to do with logs and manipulating them in your stellar magnitude group activity.